In this video, I'd like to talk about calculating the pH of strong acid solutions and of weak acid solutions. Let's begin with strong acid solutions. Consider a bottle that's labeled 0.0100 molar HNO3. Okay? What does that actually mean? Well, we know, because we've memorized it, that nitric acid HNO3 is one of our strong acids. That means if I have a solution that contains nitric acid, it is actually completely ionized to form the hydrogen ion and the nitrate anion. So what is my remaining concentration of unionized HNO3 molecules at equilibrium? Well, it's actually 0. Because it is a strong acid, there is no HNO3 remaining at equilibrium. Or I should say the other way around, because we know there is no remaining HNO3 at equilibrium, we label it as a strong acid. So what is the concentration of hydrogen ion at equilibrium? Well, that's simply equal to the initial concentration of nitric acid, which we said was equal to 0.0100 moles per liter. So to calculate the pH, I simply take pH equals negative base 10 logarithm of the hydrogen ion concentration, or the negative base 10 logarithm of 0.0100, which is equal to 2.00 molar as my pH. So, to calculate the pH of a strong acid solution, we simply assume that the acid is completely ionized. Therefore, the hydrogen ion concentration at equilibrium is simply equal to the initial concentration of HA. So we can combine that with some interesting stoichiometry problems like this one. Dichlorine heptoxide reacts with water to form an aqueous solution of perchloric acid, which we know is a strong acid. Let's calculate the pH let's calculate the pH of a solution formed by reaction of a specified quantity of reactant in enough water to make a specified final volume. So let's begin by writing the equation. Dichlorine heptoxide reacts with water to form perchloric acid, HClO4 aqueous. To balance that equation, I will simply put a 2 there. My pH I know, which is what I'm trying to find, is the negative base 10 logarithm of the equilibrium concentration of hydrogen ion, which, because perchloric acid is a strong acid, is equal to the negative base 10 logarithm of the initial concentration of perchloric acid. So now it simply becomes a stoichiometry problem to determine the initial concentration of perchloric acid. Notice this works because perchloric acid is a strong monoprotic acid, and I can see from the equation that for every 1 mole per liter of perchloric acid I start with, I will get 1 mole per liter of hydrogen ion. So let's just calculate the hydrogen ion concentration. I'll start with my mass of dichlorine heptoxide divided by the molar mass to give me moles of dichlorine heptoxide I'm starting with, but I need to multiply that by a mole ratio of 2 moles of perchloric acid formed for every 1 mole of dichlorine heptoxide times 1 mole of hydrogen ion produced for every 1 mole of perchloric acid. And I'll divide that by the final volume to give me 5.47 times 10 to the negative third molar as my hydrogen ion concentration. So the pH of the solution is simply the negative base 10 logarithm of that concentration, or 2.66. So here's an example of how we can calculate the pH of a solution of a strong acid based on composition. Now let's talk about calculating the pH of a weak acid solution. This is a little bit more complicated. Let's consider 1 molar hydrofluoric acid, for which Ka is given. Let's write the equation for the ionization in water. You can either show HF giving away a proton to water to form the hydronium ion and fluoride, or if you wish, you may equally well abbreviate that as HF aqueous in equilibrium with H plus aqueous plus the fluoride anion. The Ka expression is simply Ka equals the concentration of the hydrogen ion times the concentration of the fluoride ion divided by the concentration of unionized hydrofluoric acid. To calculate the pH, all we need to do is to find the equilibrium concentration of the hydrogen ion. Okay? Well, we've done this problem before. We learned in chapter 13 how to solve a problem like this, where you're given an equation for which you know the value of K, you're given the initial concentration of a reactant, and you simply solve for the equilibrium concentration of the products. We have done this before, okay? And the tool we used, you'll recall, is the ice table, okay? So let's set up an ice table for this reaction. My initial concentration of hydrofluoric acid is 1.00 molar. Now, you may think the initial concentration of hydrogen ion prior to ionization is 0, but it's not. Remember, you've got 1.0 times 10 to the negative 7th moles per liter from the background ionization of water. But that's almost always going to be so small as to be negligible, so we'll say it's approximately equal to 0. The fluoride concentration is 0. I will call my change in concentration of HS minus X, my increase in concentration of H plus and F minus plus X. So this becomes 1.00 minus X, X, X. Ka equals H plus, F minus over HF equals X squared over 1.00 minus X equals 7.2 times 10 to the negative 4. Now, you may think that this requires solving a quadratic formula, but remember the simplifying approximation. When K is very small, we can assume that X is going to be negligible in comparison with whatever we added or subtracted to. So we are going to cancel that in the denominator, and that gives us the following. X equals the equilibrium concentration of hydrogen ion equals the square root of the initial concentration of the acid times Ka, or 0.027 molar as my equilibrium concentration of H+. Now, you may ask the question, is the simplifying approximation always valid, or are there times when it's not? Well, there are times when it isn't, and we're going to use what's called the 5% rule. The general rule is that if, see if I can undo that. I guess not, that's okay. If the quantity that you are canceling, X in this case, is less than 5% of the quantity that you are adding or subtracting it to, then it is legit. So let's check and see if it actually is. So 0.027 moles per liter divided by 1.00 moles per liter times 100 equals 2.7%. That's less than 5%, so we're good. So to calculate the pH, we simply take the negative base 10 logarithm of 0.027, or 1.57, as my pH. So this, my friends, is how you use an equilibrium expression to calculate the equilibrium concentration of the hydrogen ion, and therefore the pH in a solution of a weak acid. If you'd like to try this on your own, you can, but it's just the same thing we did, so let's move on. Okay, here, by the way, is a table of Ka values of common weak acids. You have this available to you whenever you need it. Here's a more complicated problem. Calculate the pH of a solution that contains 1 molar HCO2H, which is formic acid, for which Ka is given, and 1 molar hypobromous acid, for which Ka is given as well. Also calculate the concentration of hypobromite in this solution. Well, we have a solution that contains equal molar concentrations of 2 weak acids, but look at the magnitudes of Ka. Formic acid, the first one, is 100,000 times stronger in acid than hypobromous acid. So what we're going to do, in terms of calculating the pH, is ignore the hypobromous acid and assume only formic acid contributes significantly to the equilibrium concentration of H+. Okay, so let's first just consider the ionization of formic acid to form H++ HCO2-. I'm just going to jump ahead to the result. We don't need to write out the ice table for all these. I'm simply going to say Ka equals X squared over 1.0 minus X equals 1.8 times 10 to the negative 4th. X is equal to the concentration of hydrogen ion is equal to the square root of 1.0 times 1.8 times 10 to the negative 4th equals 0.013 molar. I don't need to do the calculation. I can easily see that 0.013 molar is less than 5% of the initial concentration. In fact, it's 1.3%, so the approximation was justified. So the pH of the solution is to the negative base 10 logarithm of 0.013, or 1.87 as my pH. So that's the first part of the problem. The second part says, well, I know there's hypobromous acid in there, so I know there's going to be some hypobromite anion. How do I calculate the equilibrium concentration? Well, that's a little more complicated, but once again, we're good at solving equilibrium problems, so let's go ahead and do that. I'll write my equation for the ionization of hypobromous acid. I will set up an ice table. ICE, my initial concentration of hypobromous acid is 1.0 molar. Now, pay attention. The initial concentration of hydrogen ion is not 0, and it's not 1.0 times 10 to the negative 7th. It is the concentration of hydrogen ion that was produced by the ionization of formic acid, which we just calculated as 0.013 molar. The initial concentration of hypobromite prior to ionization of hypobromous acid is, of course, 0, minus x, plus x, plus x, 1.0 minus x, 0.013 plus x, x. I'll plug these into the Ka expression. Ka equals the concentration of hydrogen ion times the concentration of hypobromite anion divided by the concentration of hypobromous acid, which is 2.0 times 10 to the negative 9th. When K is this ridiculously small, you don't even need to question the simplifying approximation. It's always going to be valid. So I'm going to cancel x when I'm adding it to or subtracting it from anything. So that's both the numerator and denominator. So that simply gives me x is the concentration of the hypobromite anion is equal to 1.0 times Ka divided by my initial concentration of H plus, or 1.5 times 10 to the negative 7th molar as my concentration of hypobromite. Okay? So another example of how we can use the ice table to calculate equilibrium concentrations. Okay, this leads to the concept of what's called percent ionization. Percent ionization is another way to express the equilibrium condition. Once you've put an acid in water, once it's ionized and achieved equilibrium, you can express that equilibrium position in terms of concentrations or pH, but you can also express it in terms of percent ionization. And percent ionization is defined as the amount of the acid that's ionized at equilibrium in moles per liter divided by the initial concentration, also in moles per liter, times 100. So this essentially becomes the equilibrium concentration of hydrogen ion divided by the initial concentration times 100. And what you'll notice is that this is the exact quantity we were calculating when we were checking to see if the 5% rule was valid. It's x divided by the initial concentration, why is that all the way down there, times 100. So here's an interesting problem. Calculate the percent ionization of 1 molar acetic acid and 0.01 molar acetic acid. How does the percent ionization of an acid depend upon the initial concentration? This is really interesting. We're starting with solutions of the same acid, acetic acid, so we have the same value of Ka, but we have different initial concentrations. How will this affect the pH and the percent ionization? Well, let's see. So for each of these, I can write the equation. Acetic acid ionized to form the hydrogen ion plus the acetate anion. For A, Ka equals H plus, CH3CO2 minus over CH3CO2H, so this is the same for both, equals x squared over 1.0 minus x equals 1.8 times 10 to the negative fifth. I looked that up in the table of Ka values. X is equal to the hydrogen ion concentration equals the square root of the initial concentration of the acid times Ka for 0.042 molar. Sorry, 0.0042 molar. My pH is the negative base 10 logarithm of that. I'm going to go. Let's make the video. Profe came in to say hi. Or 2.37. The percent ionization, let's highlight these. The percent ionization is the equilibrium concentration of hydrogen ion, 0.0042 molar, divided by the initial concentration times 100, or 0.42% ionized. So a bit less than half of 1% of the acetic acid molecules are ionized. Now, let's compare this to a solution of acetic acid that is diluted by a factor of 10. Okay? Well, I'm going to skip over a lot of stuff because it's basically the same thing. X squared over 0.010 minus x equals 1.8 times 10 to the negative fifth. Again, I'll make the simplifying approximation, which should be valid, but we'll see. X equals the hydrogen ion concentration equals 0.010 times 1.8 times 10 to the negative fifth is equal to 4.2 times 10 to the negative fourth molar hydrogen ion. That gives me a pH of 3.37, which is significantly higher, meaning a less acidic solution, which makes sense because we were starting with a lower concentration. In fact, it's higher by a power of 10. Pardon me, the pH is higher by a value of 1, which means it's less acidic by a factor of 10. But now let's look at the percent ionization. Watch this. The percent ionization is 4.2 times 10 to the negative fourth molar divided by 0.010 molar times 100, or 4.2% ionized, which is almost counterintuitive. We diluted our initial concentration of acetic acid by a factor of 10. It was less acidic, but the percent ionization increased dramatically. Why is that? Well, let's think about that. This is actually Le Chatelier's principal problem. If I write my Ka expression, Ka is the hydrogen ion concentration times the acetate concentration divided by the acetic acid concentration. That holds no matter what. If I were to take a solution at equilibrium and then suddenly dilute by a factor of 100, then Q is equal to the equilibrium concentration of hydrogen ion divided by 100 times the equilibrium concentration of the acetate ion divided by 100 divided by the equilibrium concentration of the acetic acid concentration divided by 100, or Ka over 100, which is less than Ka. If Q is less than Ka, then that must mean we have to shift to products, which means that the percent ionization increases. So what we see is that when we dilute a solution of weak acid, the percent ionization goes up. Now, can we use the percent ionization or pH to calculate Ka? Yes, it turns out you can, because if you know the pH or percent ionization, that lets you calculate the equilibrium concentration of hydrogen ion, from which you can calculate Ka. This is similar to the easier, quote, equilibrium problems we did in chapter 13. So a solution of bromoacetic acid, for which the initial concentration is given, has a pH of 1.51, calculate Ka. Well, I'm going to abbreviate bromoacetic acid as HA. Here's an equation to represent the ionization. I know my equilibrium concentration is 0.75 moles per liter. Since I am given the pH, I can calculate the equilibrium concentration of both the hydrogen ion and of the conjugate base. So, equilibrium concentration of hydrogen ion, which is equal to the equilibrium concentration of the conjugate base, because they're formed in a 1-to-1 mole ratio, is 10 to the negative pH, or 10 to the negative 1.51, or 0.031 moles per liter. I know the initial concentration of the weak acid, but I don't necessarily know the equilibrium concentration. I'll have to do that by subtraction. My equilibrium concentration of HA is equal to the initial concentration minus the amount that undergoes ionization. But because there's a 1-to-1 mole ratio, the decrease in concentration of HA is equal to the increase in concentration of hydrogen ion. So I'll simply subtract the equilibrium concentration of H+. So this is 0.75 moles per liter minus 0.031 moles per liter, or 0.72 moles per liter as my equilibrium concentration of HA. To solve for Ka, I simply plug it into the Ka expression. Ka is H plus times the concentration of conjugate base divided by HA. These are all equilibrium concentrations. 0.031 quantity squared over 0.72, or 1.3 times 10 to the negative third. Okay? So this shows an important principle, and we're actually going to do this in the lab. If you know the initial concentration of your weak acid, and if you can measure the pH at equilibrium, that gives you sufficient information to calculate the value of Ka. One final problem that involves percent ionization is a little more complicated. An acid HX is 12% ionized in water. If the initial concentration is 0.3 molar, calculate Ka. Never hurts to start by writing an equation to represent the ionization, or to write Ka expression. This will always get you some partial credit. I'm given the percent ionization, so let's write out the equation of percent ionization. That is simply the equilibrium concentration of hydrogen ion divided by the initial concentration of HX, and we're told that that is 12%. So, my equilibrium concentration of hydrogen ion, which is equal to my equilibrium concentration of the conjugate base, is equal, by rearrangement, to 12 over 100 times the initial concentration of HX, which is 0.12 times, we're given the initial concentration is 0.30 molar, equals 0.36 moles per liter. My equilibrium concentration of acid is the initial concentration minus the amount that ionized, which is equal to the increase in concentration of the hydrogen ion, or 0.26 moles per liter. So now we can simply plug that back into the Ka expression. 0.036 quantity squared over 0.26, or 5.0 times 10 to the negative third as my value of Ka. So that's pretty much it for calculating the pH of solutions of strong and weak acids. In the next video, we will talk about equilibrium involving bases. See you then.